Bam! Mr. Tarrou. In this video, we're going to do sort of like a medium to hard level problem dealing with optimization in calculus. This is going to be in addition to some previous lessons I've done. You'll find links to that in the description below. Now, we're going to be dealing with this problem here that says a right circular cylinder is inscribed in a sphere of a radius r. Find the largest possible volume of such cylinder. That sphere. So what is that going to look like? Well, we have a circle. And now we can see I'm trying to represent a sphere. And inside that sphere, we have what we're going to be looking at is an inscribed, hopefully you can tell the difference between the white and the yellow, and maybe a little bit sloppy drawing. We have inside here an inscribed cylinder. Now we're going to find the maximum volume that this inscribed cylinder is going to possibly have inside of a sphere which has a radius which is not fixed per se, like we don't know it's equal to 5, but it does have some kind of constant, of course, radius of some value. Well, again, when we deal with optimization problems, we have to have that primary function. What is that equation, that function that you're going to try and optimize, finding its maximum or minimum value? So the volume of a right circular cylinder, of course, is area of the base. So volume is equal to pi r squared times the height. Just kind of pulling that formula out of geometry. But that's okay. I mean, it's obviously the formula of a right circular cylinder, but it's going to be a little bit confusing when we see this r here for the volume of a cylinder, and the r, which is the, radius of the sphere, because they're not the same. This is, let's see here, what color can I use? Green, maybe? Hopefully that shows up differently on the camera, or red. There we go. Let's use red. Here is the r that, or at least that's the radius of the right circular cylinder. I'm just going to call it a cylinder. And that radius is variable. So whether I draw the top and the bottom of the cylinder here, or here, or here, that horizontal distance is going to, of course, change from basically potentially down to a theoretical radius of 0 down to but not including 0, and then that horizontal distance can go open to as much as the radius of the circle. I guess the rate, you could actually have an x value, which is what we're going to call it, of 0, but then you're not going to actually have a cylinder that has any volume. Same as if x is equal to r. So we're going to call this and label it with the variable of x. So kind of think about us having an xy axis here where the center of the sphere is the, the origin. Okay, so volume of a cylinder, pi r squared times h, we're going to call r. Label that with the variable of, oh no, brand new piece of chalk down, and now 2 pieces of chalk. We're going to call that x. And now we need to figure out a better label or identifier for the height of the cylinder in context of this problem. Well, if I have the origin in the center of the sphere, then our vertical distance is going to be labeled with y, and we're really breaking down and working with this little right triangle right here. Okay, so pulling that out to the side, we have a triangle a right triangle whose hypotenuse is going to be the radius of that sphere. We have a horizontal distance of x and a vertical distance of y. Okay, so converting y into some more usable identifier for this particular function or this situation, this problem. The height of this cylinder is not equal to y. The height of the cylinder is equal to y, well, times 2, because we have a lot of symmetry here, and since the size of the both bases, the top and the bottom of the cylinder, are the same, that's going to be doubled. So the height of the cylinder is equal to 2y. Okay, well that's great. So we're looking at basically, what, 2 pi x squared times y. But here's where we need to bring in that fixed value, which if a question was about variable volume with a fixed surface area, we'd have to do some kind of substitution to bring information about that fixed surface area into the volume. Well, the only thing fixed here is that information of R. We need to not just find the volume of any right circular cylinder, we want the volume of a cylinder that's inscribed in this sphere with a radius of R. We somehow need to bring in that constant, though it's unknown, that constant value of R. Again, as we draw different versions of the cylinder, we can have different horizontal distances it takes to get to the edge of the sphere, and of course that's going to correspond with different heights of that cylinder. Well, it's a right triangle, so we have x squared plus y squared is equal to r squared. And what's going to be easier to get out? Are we going to bring the fixed unknown value of r into this equation through the variable of y or through the variable of x? Well, why would I want to solve for y and have square roots when I basically have a nice clean x squared here? So we have that volume is equal to 2 pi x squared, which is going to be, of course, equal to what? R squared minus y squared times y. And now we have volume in terms of what? Is the volume in terms of y or is the volume in terms of r? What would be more interesting? The volume of this cylinder is going to change, not based, well, it is sort of based on the radius of the cylinder, but more importantly, we're changing the shape of this cylinder inside the sphere based on that vertical distance of y, which is the distance away from the origin. So we need this. This is basically volume in terms of y. And I'm also going to go ahead and distribute all this together, because what's the next step after setting up your primary function with optimization problems? After you bring in that information about from the secondary function or that fixed value, you need to optimize it. You need to set up the first and use the first and or second derivative test to find where that function is either at its maximum or minimum. So 2 pi y times r squared, so 2 pi r squared y, and then 2 pi y times negative y squared is negative 2 pi y cubed. Okay, now we need to run this through a, find out where, for what function, or what value, excuse me, of y. Oh, and by the way, domain. What kind of values can y take on? Well, y can take on values from up to 0, where your cylinder, if y is equal to 0, you could actually kind of argue that, I'm going to say that y is going to be greater than 0. You could argue it could technically be equal to 0, but if y is equal to 0, well then you don't have a cylinder, you just have a circle. So I'm going to say that y is greater, it can be values that are greater than 0 and less than what? As this radius of r kind of rotates up to pi over 2, that value of y is going to go from a value of 0 up to a maximum value of r. But I'm not going to say that y can be equal to r because, well, then if y is equal to r, you don't have a cylinder, unless you want to say you have a cylinder with a radius of 0, but that's kind of just a line. And I don't know, maybe your teacher can argue that this is, maybe you disagree with me that this should be a closed interval. I'm going to keep it as an open interval though. If it is a closed interval, then you're just going to do sort of that extreme value test. So I'm going to work with the first and possibly second derivative test to find a sort of a, well, relative extrema, but if you only have one critical value on an interval, then that ends up being an absolute max or min. So anyway, v prime of y. I don't know if you need me to review and verbalize all my thinking on this. You may be very advanced in calculus, hopefully not wasting your time. As you take a derivative of this function, remember that while we do not know what the value of y is and we do not know what the value of r is being, for this problem, that fixed radius of the sphere. It's a constant. So you have a constant times just simply y. And you're taking a derivative, we're going to be taking a derivative with respect to y. So v prime of y is just simply 2 pi r squared. And here, just using the power rule, 3 times negative 2 is negative 6 pi y squared. And we need to find out where v prime is equal to 0. And where it could potentially be undefined, but v prime is never going to be undefined because this is really basically just a polynomial. So we have, setting this equal to 0, we have 2 pi r squared minus 6 pi y squared is equal to 0. But of course we can just add both sides by 6 pi y squared, giving us that 2 pi r squared is equal to 6 pi y squared. Dividing both sides by 6 pi, we have 1/3 r squared is equal to y squared. But I want to find the value of y that sets this derivative equal to 0, basically the critical value, which means we're going to square root both sides, and we have y is equal to, now, of course, when you introduce your own even root to both sides of a function, you have to account for both the positive and negative answer, but y can only be positive since we're defining it as being between the values of 0 and y. So we have basically the square root of 3 over 3. We have 1 over the square root of 3. Rationalize it, of course, r. Now, let me just check that. Okay, now that's our critical value. That's where our first derivative is equal to 0. If you really, and I'm sure your teacher is going to make you actually do this, if this is a critical value, that does not mean automatically, just, hey, where the first derivative is equal to 0, then this function of v is, going to have a absolute maximum, or even a relative maximum, or minimum for that matter, because this is just simply a critical value. You have to test whether or not this is a location where, well, this is a critical value for v prime, so does that mean that v of y, does it have a maximum or minimum there? Or maybe the first derivative doesn't change sign. Maybe this is just taking a rest, and it's just, for this critical value, this is just, I don't know, whatever. The function is kind of maybe rising, leveling off, and rising again. First or second derivative test. Now, there's two things you can do. You can either look at your first derivative and analyze the interval from 0 to square root of 3 over 3r, and then analyze the interval from square root of 3 over 3 r to r. So maybe, I don't know, maybe you pick something that like 1/4. I think that's somewhere between 0 and square root of 3 over 3. So maybe you do like a 1/4 or 1/5 or just, some 1/10 r and plug it into your first derivative to see if it's positive or negative. And then maybe, because obviously square root of 3 over 3 is less than 1, so maybe you take a 1r and plug it into your first derivative to see if it's positive or negative and look for that sign change and do that first derivative test. But remember when I said that this is basically just a polynomial? If we look at the second derivative, and instead of analyzing sign changes on the first derivative, take a look at the second derivative and think of the second derivative test, we have v double prime of y is equal to, this is a constant, so that is 0, and we have negative 6 pi times 2, which is negative 12 pi y. And y is defined to be a positive value. Therefore, we can say that v prime of square root of 3 over 3 r is equal to 0, and v double prime of square root of 3 over 3 r is what? Negative 12 pi times a positive number is negative. Therefore, v of y has, and now for purposes of space here, first and second derivative test identify relative extrema. However, This is the only critical value on this open interval, and therefore this isn't just a relative extrema, it's actually an absolute extrema. But if you really need to be super specific with your language, you're going to need to add something like, this is the only critical value on this open interval, and these conditions are met. Therefore, you have a location for an absolute maximum. I'm going to leave that out because I'm running out of room. So therefore, v of y has an absolute maximum. Y is equal to square root of 3 over 3r. Now, we got that validated. The question didn't ask for you to find the location or for what value of y does the cylinder have its absolute largest possible volume. It asked for the largest possible volume. So now we just have to take this value of y and plug it into our volume function and simplify it. And I'm going to try squeeze this in here because when I do my videos I like to have it all together for you on one screen. So v of square root of 3 over 3r is equal to 2 pi. I forgot my r and I ran out of time. So let's just finish this up again. We have v of square root of 3 over 3r is equal to, when you include the r in your substitution the second time, we have that 2 pi r squared times square root of 3 over 3r minus 2 pi times square root of 3 over 3r cubed. Well, of course, just have a little bit of multiplication here in the beginning. Square root of 3 cubed is going to be equal to square root of 3 times square root of 3 is 3 times that additional 1 left of a square root of 3. Our denominator has in it a 3 cubed, but of course 3 to the first divided by 3 cubed is 1 over 3 squared, giving us a denominator of 9. And finding a common denominator with our first fraction by multiplying the numerator and denominator by 3, we have a final answer of, which is the maximum possible volume of such cylinder, which is inscribed inside of a sphere with radius r. V of square root of 3 over 3r is equal to 4 pi over 9 pi. Let's try that again. 4 square root of 3 over 9 pi r cubed. I'm Mr. True. Bam! Go do your homework.